Some look through this prism, seeking clarity and definition. Anyone who's IM'd, tweeted, Facebooked, or interacted for any period of time on social media has encountered this problem. Tone doesn't translate. Luckily, or unluckily, humans have developed emoticons, smiley faces, to ease such confusions. Computers, though, don't have that kind of luxury, and when trying to develop software that can understand human language, homonyms, syntax, and tone can be a challenge, because let's face it, as the comedian Gallagher once noted, we drive on the parkway and we park on the driveway. Joining us to wade into how to teach a computer to understand us humans, or at least our language, is Katrin Erk. She's a professor of linguistics at the University of Texas at Austin. Welcome, Dr. Erk.
Thank you so much, Andrew.
So, help us to understand, why is it so difficult to get computers to understand the human language?
The basic problem is that humans have quite an unfair advantage. So humans have been growing up in the world. They learn about how things work over the years, and they develop all this knowledge of the world. And so when they understand language, they can bring all this knowledge to bear. And now compare that to the poor computers who do not have that knowledge, and we cannot reasonably expect to be able to encode that knowledge. So language processing is one of these problems that have been called AI complete, AI for artificial intelligence, meaning in order to really, really solve this problem, you would have to have all the world knowledge that humans have.
So it's a conditioning problem. We need the computer to be able to have a set of experiences and relate those experiences to what the language may confer. In other words, computers don't get the in-jokes.
They certainly don't get jokes and won't for many years, I guess. What we're trying to do right now is not so much trying to get the computer to have this experience, but trying to see how far we can get, how much we can get away with without that knowledge. One way that we can kind of fake having this knowledge is the following. There's an enormous amount of text around. Think of the web, all these documents that are available there. All these documents talk about human experience. They talk about what people have seen and heard, what they find important, what they find funny, what they find sad. And by processing this large amount of text, the more the better, we can get some sort of a weak and noisy image of this human experience. It's a very weak image, I have to say. But for some tasks, we can do quite well with that.
So what you're saying is it's more than just feeding a computer a dictionary so that it understands all the possible meanings and the variants of meanings of every word in the English language, and maybe even a little bit more than teaching it all the Shakespearean plays, but it's some combination of that plus other things. How have scientists tried to tackle this?
One part is certainly giving the computer a dictionary. But you have to understand, if you give a computer a dictionary, you're not really telling it how the world works. You're giving it some words that you describe with other words. So if I gave you a dictionary of Hindi that explained words in Hindi for other words in Hindi, then you could relate some sequence of letters to some other sequence of letters, but you wouldn't really understand anything deeper about how those words work. So, but still, this is remarkably useful given how little information that actually gives the computer. That, and as I said, having large amounts of text and just extracting how often do I see this word with other words. So if I see, say, the word dog a lot with the word bark, and maybe I also have tools that help me figure out that dog is a noun and bark is a dog, bark is a verb, then I can figure out that these things called dogs seem to often do this stuff called barking, even if I have no idea what either of those things are.
So in that way, the computer can disentangle the word bark being the action of making a sound from the noun being the substance surrounding a tree.
Yes. And for something like bark, the verb, and making the sound, and bark, the noun, that should work relatively well. So I'm working specifically in the area of lexical semantics, so trying to help the computer get a bit of a better understanding of what words mean. And so these cases of bark, those are the good cases. Those are the cases that we can do. But this task of figuring out what words mean when they have multiple senses, that is still incredibly hard after decades of working at it. So even nowadays, computers get accuracies of about 60% to maybe 80, 85, when we're lucky, 90% on this task, depending on how we define the dictionary. And you have to understand, I mean, even if that sounds good, hey, 60, 70, 80, 90%, that sounds good. If you think of a sentence that has 10 words in it, if you get every 10th word wrong, that means that in every sentence there will be a word that you misunderstand. So why is this so difficult? People tend to reuse the same word for related concepts. So think of even a word like bank. There's the bank where you put your money, then there is a data bank or a blood bank. So people reuse this word bank to mean, well, things where you put stuff. And it gets even worse with the verbs, a verb like show. So you can show me a picture, and then that's a concrete object that you show me out of your own free will, or you can show a theorem, then it's not a concrete thing that you show, or you can show your respect. That's also abstract, and then it's not even clear, do you do this out of your free will, or is that just something that you exhibit? If you show a bad sense of direction, then that's also abstract and probably not of your own free will that you show a bad sense of direction. And all these uses of the word show are related. So people just reuse the word show for all these similar things that still a computer might want to distinguish if it wants to figure out if this is a concrete object that you showed, or if you made a property of yours apparent.
And I suppose that most people would understand confusion when it comes to homonyms, words with the same sound but different meanings, or words that are worse, spelled the same but mean something different. But there's also an old acting trick. I remember when people would say, how many different ways can you say good morning? And you'd say, good morning! Good morning! And you could, just by changing your tone, the entire two-word sentence alters drastically. Do computers have a hope of dealing with that?
That is a good question. I mean, computers have a problem even with words that are not homonyms but polysemous. So when they have multiple related senses, like in the show example that I mentioned earlier. And that is even without bringing intonation into the picture. With intonation, that is actually also difficult for people to do. Probably noticed that email is sometimes a tricky medium, especially if, say, some emotional baggage. So you are angry or you're happy about something. Sometimes this doesn't really come across right over email, and then there are misunderstandings that need to be straightened out, and people will say, this is a tricky business, let's not do this over email. I think that is because intonation doesn't come across via email. So if you have something tricky to convey, you use voice. Or nowadays in social media, people try to convey this tricky business, the intonation, via emoticons or by varying spelling. So instead of saying, say, cool with 2 O's, you say cool with 10 O's. And I'm really curious to see what social media is going to produce there. If they are going to produce spelling variations that are going to solve or at least ameliorate this problem of intonation to some extent. I don't know. I mean, so far, I wouldn't say that they've solved the problem, but they have certainly made some steps towards it. Could computers pick up on that? Well, emoticons are pretty unambiguous, and you can pick up on them, and you can process them. And there is work that makes use of emoticons in tweets, in order to figure out whether the overall sentiment, say, of a tweet was positive or negative towards some statement. So these emoticons will turn out to be useful. How useful? We'll have to see.
And while to be or not to be may be the question, it's not the answer. So I'm going to turn to you and say, what is the answer that you're working on? What is your strategy to teach computers how to understand us, how to understand language?
So I'm focusing on individual words and what they mean. And as I said, I'm kind of doubtful that we have anything like a list of discrete senses in our heads, or that the computer should have that. Instead, what we can do is we can represent individual occurrences, individual uses of a word as points in high-dimensional space. So where does that space come from? That's really super simple. What you do is basically you count what other words occur in the vicinity, what other words are hanging around in the same sentence or in the same document. So you can represent each occurrence of a word as this point in space. And then some occurrences of the word may be close together in that space. So they may be similar uses of the word. Some other points may be in a completely different corner of the space. So this would be wildly different senses, like your bark as making a sound and bark the stuff on trees. But sometimes you might see uses that are not really exactly very close by, but not far away either, more like you could say a smear all the way through this high-dimensional space. So that would be a visualization of all these uses that are related and not clearly apart. And if we can do this kind of a representation, then we don't ever have to say how many senses a word has. Then we can just say, well, do we see any distinct clusters? Do we just see something like a streak all the way through space with some uses closer together, some further apart? And if you give me a new occurrence, if I can place it somewhere in this space, then I can say, well, this use of the word is kind of similar to those other uses. So maybe I can conclude that something similar is going on as in these other occurrences.
So basically what you're doing is one of two things. You're creating a frequency chart, looking at what words are often paired together, blue sky, or perhaps you're creating a series of Venn diagrams in which you're looking at which words have commonalities or which are used together, which never do, and which often have overlap. Is that right?
Yeah, if you look at different words, yes. But if you think of a single word, like the example that I gave earlier of show a picture, show a bad picture, show your respect, show a theorem, show me the road to the bank, all these individual uses of the same word, you can also picture as points in space, and they can be closer together or further apart. And then you don't ever have to kind of draw these circles that you have in the Venn diagram, because those circles would be like saying, I have distinct senses. Instead, you just have these clouds that may have clear boundaries or not. And for some words, they may have clear boundaries, and for others, not. And that then also gives us the chance to see. So are there words that are super easy for computers, like bark versus bark, and are there other words that are really nasty, both for computers and for poor lexicographers, like words like show or the verb leave, by looking at what kind of pattern do they have in this high-dimensional space.
And how successful has this strategy been? Has it been able to help a computer differentiate better?
That's hard to say. It's still early days, and it is a hard task. So we have been able to show that people can do this kind of graded annotation. So say humans, if you ask them to what extent are these two uses similar or dissimilar, they can do that. So that shows that people are able to deal with word meaning in this kind of graded way. So this we have been able to show. We have developed a series of models that to some extent can do this prediction of meaning without having dictionary senses. And other people have picked up on this. And just at the conference that I returned from yesterday, there was a new and pretty encouraging result by colleagues of mine from Darmstadt. So yeah, we are making progress, I would say.
And is this really a problem of complexity, or was it also a problem of power? Did the computers that you were working with, that you were designing software with previously, or even today, suffer from a lack of power and memory? Is having more, will that be the solution in and of itself, or a large part of it?
Yes, and that is the case for all of natural language processing. I can't hardly recall who said it, but it's very true that more data is better data. And that is true basically wherever you look in natural language processing. So if instead of 100 million words, I can deal with 2 billion or 3 billion words, then all my models will be quite a bit better. And that is true anywhere you look, in any task in natural language processing. And so we are more and more, as a field, turning to using parallel processing and more powerful machines, just because models get better, not just if you build cleverer models, but just if you throw more data at them.
Earlier in the conversation, you began speaking about artificial intelligence. Is this actually an intelligence problem, or, as we said, is it a memory problem?
You can use memory as a weak substitute for intelligence. People have actually tried to encode all that world knowledge that people have, to give it to computers, but that hasn't really worked out so far. I mean, some manually encoded resources like WordNet have been immensely helpful, but they focus on just a small portion of what it is that humans know. But if we use these meager and shallow approximations, like just reading through a couple billion words of text and extracting all these combinations of words that we can and relations between words, then we can to some extent fake it. So we can fake world knowledge by just having knowledge of what words we have found in the vicinity of other words. So in the long run, ideally, you would have actual intelligence. But for now, what we have is give me more memory, give me more data, then I can do a better job of faking it.
Teaching computers to learn, or at least to fake it. I'm Andrew Hiller for The Prism on The Voice of Russia, and I've been joined by Katrin Erk. She's a professor of linguistics at the University of Texas at Austin. Thank you so much for the insight.
And thank you.